Hi everyone, welcome back. So in this video lesson, I'm going to present to you a brief tutorial on the VSEPR theory. Now you're going to use this, after you've learned this, you're going to use this in the lab. We're going to give you an exercise where you're going to work through the same types of problems that you're going to see here and in the practice worksheets that we have in your lab manual. So basically what you're going to do is watch this video, kind of follow along. You can get the worksheets and the notes that I have here in this video on the Canvas website, so that you can write notes on it as you follow along. And then after you've watched this video and you feel like you understand it, you're going to go through the exercises we have in your lab manual. There's a set of worksheets that you're going to look at, and you're going to complete those worksheets and check your answers against the keys that we provide you. After you've done that, you'll be pretty proficient at doing this, and then you're going to come into the lab and we're going to give you sort of a quiz on it so that you can show how good you are doing this after you've practiced all this. So with that, let's get into how we do this. Again, I want you to print out the VSEPR theory tutorial packet that I have here that I'm writing all this stuff on. So go onto Canvas, print out this packet, and then follow along. So what exactly is VSEPR theory and what does it allow us to do? Well, VSEPR theory stands for valence shell electron pair repulsion theory. And we are going to learn how to use VSEPR theory to predict the three-dimensional shape of simple molecules based entirely on their Lewis dot structures. Now, VSEPR theory states that the three-dimensional shape of a molecule can be based entirely on two factors. When we look at the Lewis structure, one of the factors is the number of terminal atoms bonded to a central atom in the middle. Right, so we're going to look at a Lewis dot structure and see how many terminal atoms there are, and that's part of what we take into account when we try to figure out the three-dimensional shape of a molecule. But VSEPR theory also says that the shape is also based on the number of non-bonding electron pairs that are also on the central atom. So VSEPR theory says if we take these two things into account, right, the number of terminal atoms bonded to a central atom and the number of non-bonding electrons on a central atom, from those two things we can figure out the three-dimensional shape of a molecule. So in practice, it looks something like this. We draw a Lewis structure where we have a central atom and then we have terminal atoms connected to that central atom, or those things on the outside could be lone pair electrons, and then we add up all of those things, and then from that we determine the three-dimensional shape of the molecule. So I'll draw you a quick example of what this looks like with a real molecule, or two different molecules actually. So one of these I'll show you is H2S. Now when you draw the Lewis structure for H2S, you end up with this, where we have two terminal hydrogen atoms connected to the sulfur, which has two sets of lone pair electrons. Now, compare this with sulfur dioxide, which has two terminal atoms and one lone pair on the central atom. If we add up all of the things on the central atom, we get three things on sulfur dioxide, but four things on H2S. And that would end up giving us two different, predicted by VSEPR theory, two different bond angles here. For H2S, it's 109.5. A smaller bond angle than it is for sulfur dioxide, which is 120 degrees. So that's basically what I'm going to teach you about, how VSEPR theory predicts this stuff, and how you know what the bond angles are when you have different situations. So let's fill out this table first. If we add up the terminal atoms and lone pairs and we get the number 2, we would have an arrangement that looks like this, and we call this linear. And the ideal bond angles when we have two things attached to the central atom is 180 degrees. Now, if we have three things attached to the central atom, we get a slightly more interesting situation. We could have three atoms connected to the central atom, or we could have two atoms and one set of lone pair electrons attached to the central atom. Now, this leads to two different sort of shapes or names for different shapes that we have. So if we had three atoms connected to A, like I've shown here, that's one type of shape. But if we had two atoms and then one of those things connected to A was not an atom but a lone pair of electrons, that gets a different name because it has a slightly, as you can tell, it looks different, right? We have atoms versus lone pairs. The first one we call trigonal planar, and the second one we call bent, because that third atom isn't there. The ideal bond angles for both of these are 120 degrees. Now, if we had 4 things attached to a central atom, this is a slightly even more interesting situation, right? We could have 4 atoms, or we could have 3 atoms and 1 set of lone pairs, or we could even have 2 atoms and 2 sets of lone pair electrons. So because of this variety, we have actually 3 different shapes that we get out of this, or 3 different arrangements with 3 different names. Okay, the first one is we have all atoms connected to A. Okay, and the next one I'll draw is 3 atoms and 1 lone pair of electrons, right? So one of those atoms would be missing in this case. So we can draw the 3 atoms and then 1 lone pair. And then the last case would be where we have 2 atoms and 2 lone pair electrons, right? So 2 atoms are missing and they've been replaced by lone pairs. So these are 3 different geometries, really, and we give them 3 different names. The first one we call tetrahedral. That's where we have all atoms connected. All 4 atoms terminal atoms are connected to the central atom. But if we had 3 atoms and 1 set of lone pair, this has a different name. We call it a trigonal pyramid or trigonal pyramidal. Okay. The last one looks a lot like the bent from the bent above. We call it bent, but this bent has 109 as the bond angles, and the one above is 120. So we get a different bond angle for this. That's what VSEPR theory would predict. So what we're going to do is I'm going to outline all of these in a bigger table on the next page with all of the details, and we'll go through them a little more slowly. But this is a summary of what VSEPR theory does. And what we're going to do after we outline that table, which, by the way, you can use in the lab. There's also one in your lab manual that you can use. It's the same one we're going to do here. I just wanted to go through and fill it out with you so that you understand where that information is coming from. But again, you can use the one in your lab manual or the one that I present to you in these notes. They're equivalent. So let's go to the next page and fill out that table. And then after we do that, we'll go on and we'll do some real examples of using this on some actual molecules and molecular formulas. Okay, so let's go take a look at that. Okay, so what we're going to do here is outline the entire VSEPR theory that we are going to use in this class. So what we're going to do is start out by filling out the table, and we're going to start on the left-hand side of it, and we're going to work our way in this direction. Now, this first column that we're going to fill out is the main part of VSEPR theory. And remember, VSEPR theory is based on we're basing the 3-dimensional shape of a molecule based on 2 different things. It's based on the number of terminal atoms connected to a central atom and the number of lone pairs on that central atom. And if we add these 2 things up, from that information, we will get the different shapes that are possible for a molecule. So what possibilities do we have for the number of terminal atoms and the number of lone pairs? Well, it turns out if we're following the octet rule, we have a limited number of possibilities here. It turns out we can have either 2, 3, or 4 as possible values here. So let's write those down in the table first. Okay, so now that we have that part of the table filled out, where we can either have 2, 3, or 4 things around a central atom, we're going to now fill out the rest of the table. So we're going to look at the different combinations of terminal atoms and lone pairs on the central atom, and then we'll see what the arrangement would be like predicted by VSEPR theory. So we're going to look at sort of a picture of what the arrangement would look like, and then we're going to determine what the geometry would be like as far as the bond angles go. So we're going to look at the name of the geometry and then what are the bond angles in each case. So as we're going through this, the first thing I want to mention is that the basis of VSEPR theory is that when you have terminal atoms and lone pairs on a central atom, that the electrons that are connecting the atoms or acting as lone pairs on a central atom, those electrons all want to repel each other. So everything wants to get as far away from the other sets of electrons as possible in order to maximize the amount of space that is between them. So that's the basis of VSEPR theory. So as we're going through it, let's talk about that. Let's think about where things would be to get as far away from each other as possible. So let's start off by looking at the case where our Lewis dot structure has two terminal atoms and no lone pairs on the central atom. What does VSEPR theory predict for the arrangement of the atoms around the central atom A? So I have a central atom A here, and if the two terminal atoms are going to repel because of the bonds in them, they want to get as far away from each other as possible, then the geometry predicted by VSEPR theory is a linear geometry, and that's where the bond angles are 180 degrees. Now things get a little bit more interesting when we add up the terminal atoms and lone pairs and we get the number 3. When we have 3 things around a central atom, it turns out that there are 2 possibilities we can get. We can have all of the things being terminal atoms, so we get 3 terminal atoms and 0 lone pairs, or we can get 2 terminal atoms and 1 lone pair. And because of this, we actually get 2 different shape possibilities or arrangements that we can have around a central atom. So in the first case here, where we have all 3 things around the central atom being atoms with no lone pairs on the central atom, it would look something like this, where we have A in the middle and then 3 Y atoms connected to A on the outside. This geometry is called trigonal planar, and because all of the atoms Y are going to maximize the space between them, the bond angles turn out to be 120 degrees. Now the second case is where we have 2 terminal atoms and then 1 lone pair on the central atom. So instead of having all terminal atoms, we have a lone pair here. This is called bent, and the bond angles are predicted to be 120 degrees. So just to recap this one, we have 3 things around a central atom, and we can have either all of those things being terminal atoms, so we have 1, 2, 3. This is called trigonal planar, and the bond angles are 120 degrees. We could also have the situation where we have 2 atoms and then 1 lone pair. This is still 3 things around a central atom. So therefore we still have 120 degrees as the bond angles, but we call the shape bent because we only have 2 actual physical atoms connected to A. The third thing here is a sort of quote-unquote invisible set of electrons, or a lone pair of electrons. Now we can't see those directly, we can see the atoms connected over here, and therefore we call it bent, okay? And notice both of these are 120 degree bond angles. That's because in both cases, we have 3 things around the central atom. Now let's look at the next case where we have 4 things around the central atom. So we can have a combination of terminal atoms and lone pairs, but whatever that combination is, it has to add up to 4. And it turns out we get 3 different possibilities for those. So let's go through each of those 3 possibilities. So the first possibility is all 4 things are terminal atoms connected to a central atom. So I'm going to draw that here. We have Y, 4 of them, connected to A in the middle. This is called a tetrahedral geometry, and it looks in 3 dimensions like a pyramid, like a tall pyramid, where A is a little bit up from Y, and then we have Y's pointing up and down at the base. This is called tetrahedral, and the bond angles here between all of the atoms Y are all the same. They're all 109.5 degrees. We could also have the situation where one of those Y atoms is not an atom. It's actually a lone pair of electrons. So we have 3 atoms and 1 lone pair. This is like a pyramid with the top cut off. We call this a trigonal pyramid or trigonal pyramidal. And the bond angles here haven't changed, right? We're just replacing one of the atoms with a lone pair. So the bond angles are still 109.5 degrees. Now the last case here is where we have 2 sets of lone pairs and 2 atoms. So the number still adds up to 4, but we have 2 and 2 instead of 3 and 1 or 4 and 0. This is called bent. But notice this bent has 109.5 degree bond angles, whereas the other bent was 120 degrees. So let's summarize this table. If we have 2 things attached to a central atom, the bond angles are 180 degrees. If we have 3 things on the central atom, it's 120 degrees. And if we have 4 things, it's 109.5 degrees. So that's basically VSEPR theory in a nutshell. Now, again, this table is in your lab manual with all of the same information, but I wanted to show you that actually if you just kind of go through and think about what this table is saying, it's very logical, and you could probably put a table like this together yourself without having to rely on the table in the lab manual if you wanted to. Now, you can use that table in the lab manual when you go and you do your post-lab quiz in the lab. You can use that table to reference all of this information. But when you get to the exam, you're going to want to have that memorized as well as possible. So anyhow, let's go to the next page. Let's do some examples with drawing Lewis structures and then using VSEPR theory to predict the three-dimensional shape of the molecules that we get from those Lewis structures. So let's go to the next page. Okay, so let's see how to apply this VSEPR theory to some different example molecules. So in the packet that I have on Canvas on the next page, you'll see these different examples, or a couple of pages of these. We're going to go through each of them. And this looks exactly like, or at least very similar to, the practice worksheets you have in your lab manual. So once you've gone through a couple of these, you'll see how to do the ones in the lab manual. Then you will try those and check your answers against those, so that you've had enough practice when you go into the lab and you do the quiz, you should be able to get all of them right. So let's get started doing this. The way that this works is we're given some formulas for different molecules. And what we want to do is come up with the shape. The first step in that is actually drawing a Lewis dot structure for each of these. So that's sort of the first thing I want to go through, is actually drawing an accurate Lewis dot structure. So to get started drawing a Lewis dot structure, the first thing that we have to do is we have to add up all of the valence electrons that are present in that structure. So where we get the valence electrons from is the molecular formula. We look at the atoms in the molecular formula and we add up the valence electrons that each atom brings to the structure. So we look at the group number for the atom and we say, okay, what group is it in? How many valence electrons does it have? And then we add all of those up. And this will be the number of valence electrons that we have to work with. We can't have any more or any less in our structure. So let's look at the first example I have over here, which is the water molecule. Water has the formula H2O. So we have to add up all the valence electrons in water. We have to look at hydrogen and oxygen, what group those atoms are in, and how many valence electrons each one has. So we know oxygen is in group 6, so it has 6 valence electrons, and hydrogen is in group 1, so each hydrogen has 1 valence electron. We have 2 of them. So if we add up all of this, 6 plus 2 is 8. So we have 8 valence electrons to work with drawing our Lewis dot structure. So now we're actually going to start drawing the structure itself. And where we start with the Lewis structure is we have to have a central atom. So what we're going to do is we're going to draw the central atom and we're going to place it, of course, in the center. Now the question is how do we know which atom, if there are more than one atom, which one is the central atom? Well, that's actually pretty easy for us to figure out looking at the molecular formula. The central atom will always be the first atom written in the formula, with one exception, hydrogen. It turns out hydrogen can never be a central atom. So if hydrogen is written first, we just go to the next atom after hydrogen. So it's either the first atom that's written or the one after a hydrogen atom. That will always be the central atom, okay? So let's start off drawing our Lewis structure by picking the central atom here for water. So notice we have hydrogen written first. That can't be the central atom. So the central atom has to be the one after hydrogen, so it must be oxygen. So now that we have the central atom placed, let's also connect the terminal atoms. So this is step 3. We're going to connect all of the terminal atoms to the central atom using a single bond. So for water, we have 2 hydrogen atoms that are our terminal atoms. We're going to connect these to oxygen using single bonds. And the original initial placement of these terminal atoms, you might want to end up revising later. So I always suggest drawing your Lewis structures in pencil and then making corrections with an eraser. So let's connect our 2 hydrogen terminal atoms to the oxygen using single bonds. So now that we have the terminal atoms connected, we're on to the 4th and last step in drawing our Lewis structure. And this is usually where people have issues. Up until now, it's pretty straightforward. What we're going to do in the 4th step is we're going to do something called completing the octet. And we're going to complete the octet, or 8 electrons around each atom. And we're going to follow kind of a very specific process here. We're going to complete the octet, first of all, using all the remaining electrons that we have available from our valence count. We're not going to exceed that number, and obviously we're not going to not use all of them. So we're going to complete the octet around all the atoms. Now we're going to follow this very specific process. We're going to do the outside atoms first before we do the inside atoms. So we're going to work our way from the outside in. If you don't do it this way, you won't get the right Lewis structure. The other thing to remember is that hydrogen has a maximum of 2 electrons, rather than the other atoms, which have a maximum of 8. Hydrogen's only 2. And then the last thing to remember is that each bond that we draw is worth 2 electrons. So if a single bond, it's 2 electrons. If we have a double bond, of course, that is 4 electrons. So let's do this. Let's complete the octet around each of the atoms in water, working from the outside in, using up all the electrons and thinking about the bonds as being 2 electrons each, with hydrogen having a maximum of 2 electrons. So let's see how many electrons we've already used just by drawing the terminal atoms bonded to the central atom. We have 2 bonds already placed on water. So each one of these bonds is 2 electrons. So we've already used 4 electrons in the bonding. So that means we have 4 electrons remaining in our valence electron count. Now what we're going to do is complete the octet, going from the outside atoms to the inside atom. Okay, so let's start. Outside atoms, terminal atoms, we have hydrogen. Let's complete the octet around hydrogen. Well, remember, hydrogen can only have 2 electrons around it. So actually, in this example, hydrogen's already at its maximum. It's 2 electrons because of the bond. So if it has these 2 electrons, hydrogen's done already. And this hydrogen is done as well. So we can't put any more valence electrons around the terminal hydrogens because they're full. Now, what do we do with the 4 electrons? We still have 4 left, right? Well, those have to go. If they can't go on the terminal atoms, that means they have to go on the central atom. So let's place them around the central atom in pairs. So we have 4 total electrons remaining. Let's put 1 pair over here. So that's good. We've now used a total of 6 electrons. Let's put another 2 on it, and that is all of our 8 electrons. So we've completed the octet now around oxygen. Right? We've used all 8 electrons. We have 2, 4, 6, 8. All of the atoms have an octet, right? Oxygen has 8 around it. Hydrogen has 2 each. So this is our Lewis structure for water. So that's the process for drawing a Lewis structure. First, we add up the number of valence electrons, right? That's based on the group number. Then we draw a central atom in the middle, right? Remembering that hydrogen is never central, but otherwise it's the first atom in the formula. Then step 3, we're going to connect all the terminal atoms to the central atom using single bonds. Okay, that's step 3. Then the 4th step is we complete the octet around all of the atoms, going from the outside in, so the terminal atoms first. Remember, hydrogen, maximum of 2, and then each bond is worth 2 electrons. And then you'll end up with if you do that properly, you'll end up with an accurate Lewis structure. Now what we're going to do is finish up with the rest of using the VSEPR theory to fill out the rest of this table. So we have to add up the number of terminal atoms, the number of lone pairs on the central atom, and then from that we'll predict the molecular geometry, the bond angles, and then we'll talk a little bit about the polarity stuff as well. So if we look at the structure we've drawn, we see that we have 2 terminal atoms, right? We have 2 hydrogens. Those are both terminal. And then we look at the central atom to count up the number of lone pairs, and we see we have 2 there as well. So we have the 2, 2, and if you look at the table we made up on the last page, you'll see that predicts, by VSEPR theory, the bent geometry with 109.5 degree bond angles. This is called bent, and we're going to write that down in our table here. Now, because I know bent actually looks bent, I'm going to also redraw my Lewis structure to reflect that. Now, you don't need to do that, and actually the answer sheets for the worksheets don't show it that way, but I like to show it because it's a little more accurate representation of what the structure is. So I draw it kind of bent there. And then I'm going to put in the bond angles also as 109.5 degrees. Those are the ideal bond angles for a bent geometry. Now let's talk about bond polarity. What are we going to put there? The bond polarity column is where we're going to show how the bonds are polarized towards the more electronegative atom. And remember, you learned how to do that by drawing arrows from the less electronegative atom towards the more electronegative atom with a little plus sign next to the more electropositive atom. Now, how are you going to remember which atoms are more electronegative than others? Well, you're not going to remember. You're actually going to look those values up on the Pauling electronegativity scale That is in your lab manual. It will also be included on the post-lab quiz that you get. You will always be given that table. An exam, for instance, you'll be given that information. So you're going to look up the values, and in this case for water, you'll see that the value for hydrogen is smaller than the value for oxygen. So I've drawn the arrows towards the oxygen, which is the more electronegative atom, and then I put this little slash over here next to it to show that that's the more electropositive atom. Now we're coming to the last column here, which is the molecular polarity column, where we're going to determine if the molecule is polar or not. And I want to give you a really easy way to look at a Lewis structure and quickly be able to assess that. It turns out that a molecule's polarity can be easily determined from the Lewis structure, and this is how we do it. We say that a molecule is polar if one of two things are visible on the Lewis structure. So you look at the Lewis structure, and one of the things that will make that Lewis structure polar is if the terminal atoms are not all the same as each other. So you look at the terminal atoms, if they're all the same, that doesn't make it polar. But if the terminal atoms are not all the same, so if one of them is different than the other, that will make the molecule polar. Now that's not the only thing that can make a molecule polar. Another thing that makes a molecule polar is if there are lone pair electrons on the central atom. If you look at your Lewis structure and you see that there are any lone pair electrons on that central atom, that makes the molecule polar. So just to recap, a molecule is polar if the terminal atoms are not all the same as each other, or there are lone pair electrons on the central atom. Now you don't need both of these to happen to make a molecule polar, just one or the other. So let's look at water and try to determine if water is polar or not. So yes, it is polar. Why? Notice there are lone pair electrons on the central atom. So while the terminal atoms in water are identical with one another, hydrogen, the molecule water is still polar because of the presence of lone pair electrons on the central atom. All right, so let's move on to the next example. Let's look at CH4. This is actually called methane. Now, what I want you to do is go through the first couple of steps yourself. First off, you're going to try to figure out how many valence electrons methane has based on the formula. And then I want you to also figure out what are the central atoms and what are the terminal atoms, given this is the molecular formula. And then start off by connecting the terminal atoms to the central atom, and then we'll go from there. Okay, so carbon is in group 4, so we have 4 valence electrons. Hydrogen is in group 1, and we have 4 of the hydrogen atoms, so that brings 4 valence electrons in. If we add all these up, we get a total of 8 valence electrons. And we know that carbon is the central atom because it is first in the formula. Now we're going to move on to the next step, step 2 in this, which is we're going to connect the terminal hydrogen atoms to the central carbon atom with a single bond for each. Now what we're going to do is verify that the octet is complete for all of the atoms and make sure we've used up all of the valence electrons. So we have a total of 8 valence electrons to use, and we have 2 in this bond, 2 in this bond, 2 in this bond, and 2 in this bond. So that's a total of 8 valence electrons in the formula. We have an octet around carbon, so carbon is full, and each hydrogen has its 2 electrons. So we've successfully drawn an accurate Lewis structure. Now we're going to move on to the VSEPR theory component. So we're going to fill out the column for the number of terminal atoms, the number of lone pairs, and then the shape as well as the bond polarity and the molecular polarity. So go see if you can fill out these columns accurately and double check yours against mine that I'm about to show here. Okay, so we see that we have 4 terminal atoms and no lone pairs on this central atom. And if you look up 4, 0 in the table we completed, you'll see this is called the tetrahedral geometry, giving a set of bond angles that are 109.5 degrees. Now, to complete the bond polarity, we note on the Pauling electronegativity scale that hydrogen is less electronegative by a small amount than carbon. So we're going to write the arrows drawing from hydrogen towards carbon in each case. So we're going to point our arrows that way for each of these. Now let's also determine the molecular polarity. We look at the terminal atoms and we see they are all identical with one another. So that doesn't make the molecule polar because they're all identical. We also look to see if there are any lone pair electrons on the central atom, and we don't find any. So the molecule is not polar. So let's move on to the next example, which is ammonia, which has the formula NH3. Go ahead and see if you can determine the number of valence electrons, the Lewis structure, and try to predict, using VSEPR theory, the shape and the bond angles, as well as the polarity. Okay, so we have nitrogen, which has 5 valence electrons, and we have hydrogen, which has 1 each, and there are 3 of them. So we get a total of 8 valence electrons. Nitrogen is the central atom, so we're going to connect our terminal hydrogens to the nitrogen. And now if we stop here and look at how many electrons we've used, we see 3 bonds, and each bond has 2 electrons in it. So we've used 6 electrons. We still have 2 more electrons to place. We can't place them on the terminal hydrogen, so we have to place them on the central atom, which is nitrogen. So we get 3-1 here, which is a trigonal pyramid. And the bond polarities show that nitrogen is more polar, more electronegative, I should say, than hydrogen. So we draw our arrows from hydrogen to nitrogen in each case. And we also have to specify the molecular polarity. Notice that the terminal atoms are all identical with one another, but we do have the presence of the lone pair on the central atom. That presence of the lone pair makes the molecule polar. So we can say, yes, the molecule is polar. So those are 3 pretty basic examples. Let's go to the next page and look at a few other things that can happen, including double bonds and charges on ions. All right, so let's do our next example here, which is the molecule called formaldehyde. We have 3 different atoms here. We have a carbon, which is in group 4, so it has 4 valence electrons. We also have hydrogen, and there are 2 of them, and each one brings 1 electron. So we have 2 times 1 for the valence electrons. And then we also have oxygen. Oxygen is in group 6, so it has 6 valence electrons. So if we add all of these up, we get a total of 12 valence electrons. Now we're going to draw the Lewis structure, and as we're drawing this, it's a really good idea, especially when you're seeing how you revise these, to draw these in pencil, because you're probably going to have to erase them and change them. And pen, you're going to have to kind of scratch it out. It makes it really messy. So start off with pencil. Now the first thing we do, of course, is we determine the central atom. Now notice the formula here. We have carbon written first, so that tells us the central atom is carbon. So let's draw a carbon, and then we're going to connect the terminal atoms to that carbon. We have an oxygen, and we have 2 hydrogen atoms connected to that. Those are our terminal atoms. Okay, so that's our first step, right? We get the terminal atoms connected to the central atom. Now what we have to do is complete the octet around the terminal atoms. Now hydrogen can have a maximum of 2 electrons. So we have these 2 hydrogens here. We can't put any more electrons around them because they already have a single bond to them, and that single bond has 2 electrons in it. We can, however, put more electrons around the terminal oxygen, and we're going to complete the octet. So we already have the 2 electrons in that covalent bond, the single bond there. But if we have another 2, another 2, and another 2, that gives us a total of 8 valence electrons around oxygen. So now it has an octet. So let's take a look at what's going on here. How many electrons have we used? Well, we've used 2, 4, 6, 7, 8, 9, 10, 11, 12. We've used a total of 12 valence electrons putting this structure together. Now, we do have a problem, however. Notice the carbon in the center does not have an octet. It only has 2, 4, 6 electrons around it. That's a problem. So let's write that down as a note here, that this carbon atom does not have an octet. So it doesn't have an octet. How do we fix that? Well, we fix that by changing the structure. What we're going to do whenever we see a central atom that doesn't have an octet is we're going to end up forming double bonds from the outside in, like this. We're going to take some electrons from oxygen, and instead of moving them off of oxygen, we're going to share them between carbon and oxygen. That gives us a double bond. So if we redraw the structure over here like this, where we still have carbon in the center, an oxygen connected to it, and then we have our 2 hydrogen atoms, we now have an additional bond, a double bond between that carbon and the oxygen. Now what I did here is I used these electrons to make that double bond. So the oxygen doesn't have that lone pair on it anymore. It only has the other two lone pair electrons. So this is the correct Lewis structure for formaldehyde, where we have the central carbon doubly bonded to the oxygen, and then all of the atoms have an octet. Notice carbon has 2, 4, 6, 8. Oxygen also has 2, 4, 6, 8. And then the hydrogens have 2 each. So now we can complete, now that we have an accurate Lewis structure, we can complete the VSEPR theory table. How many terminal atoms do we have? 3. How many lone pairs do we have on the central atom? 0. So what geometry is this? If you go look it up, it's called trigonal planar. And the geometry, the bond angles for trigonal planar are 120 degrees. Okay. So now we can do the bond polarities. We have carbon in the center, and that is less electronegative than oxygen. So we can draw an arrow towards the oxygen, and then we find also that carbon is less electronegative, or sorry, is more electronegative than hydrogen. So we're going to draw our arrows towards carbon like that. And that's the bond polarity diagram. Notice I didn't show the double bond on the bond polarity diagram. We're not trying to show bonding here. We're just showing which way the bonds are polarized, not how many bonds there are. So that's the bond polarity. Now let's do the final thing. Is this molecule polar or is it nonpolar? So we look at it, we see, okay, what about the terminal atoms? Are the terminal atoms the same or are they different? Notice that we have two different types of terminal atoms here, oxygen and hydrogen. That makes this molecule polar. So we're going to write yes. Okay, so now that we've done that example, let's try another one. We have H2S here, but I think I have a better example we can try. Let's try this one instead, NO2Cl. So give this one a shot. See if you can come up with an accurate Lewis structure and then predict the VSEPR theory stuff for it. So let's first start off by adding up the valence electrons for all of the atoms. We've got nitrogen, that's in group 5, so it has 5 valence electrons. We have oxygen, and that is in group 6, so we have 2 of them. That's going to give us a total of 12 valence electrons. And then we have chlorine. Chlorine is in group 7, so it has 7 valence electrons. So we add all of these up, and we get to 24 total valence electrons. All right, so now we're going to draw the Lewis structure. First thing we've got to do is determine the central atom. Nitrogen is written first in the formula, so nitrogen will be our central atom. So I'm going to draw a nitrogen there, and then we're going to connect all of the other terminal atoms to that nitrogen. So we've got an oxygen here, another oxygen because there are 2 of them, and then we have a chlorine. Okay, so now what we have to do is complete the octet around the terminal atoms and then move our way in if we have any left over. So let's complete the octet around the terminal atoms. So if I complete the octet, that means I have to put 3 lone pairs around each of these terminal atoms to give it a total of 8, right? Because each one already has a single bond, which is 2 electrons, and then as I place these other pairs, that adds up to 8. So if you look at it now, we've got 8 electrons around each of the terminal atoms, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Great. How many electrons have we used? Well, if we have 3 terminal atoms and each one has 8 around it, we've used 8, 16, 24 valence electrons. Now notice here, that's all I have available is 24 valence electrons. Now you might notice there's a problem, right? Notice that the nitrogen in the center doesn't have an octet. It only has 6 electrons, right? Now that's a problem, right? We need to have an octet around that nitrogen. So we solve this problem again by making double bonds between terminal atoms and the central atom. Now this is where we have a little bit of a conundrum, right? We have 2 different types of terminal atoms. We have oxygen and we have a chlorine. And it turns out it does matter when you form double bonds what type of atom you choose to form those double bonds from. And it turns out that we're not going to form double bonds to atoms that are in group 7 or hydrogen. So chlorine is in group 7. We're not going to form a double bond with the chlorine. We're going to form a double bond instead with the oxygen. So I'm going to borrow some electrons from oxygen and share them between oxygen and nitrogen, and then draw the new Lewis structure. Okay, because we're borrowing those electrons from oxygen and sharing them with nitrogen, we're going to have a double bond between nitrogen and oxygen, and then we're going to take that lone pair off of the oxygen, leaving only two behind. The rest of the lone pairs on all the other atoms stay the same. So we have two lone pairs on that top oxygen, and then three lone pairs on the other one, and then three on the chlorine. Okay, so let's complete the VSEPR picture for this Lewis structure. How many terminal atoms do we have? 3. How many lone pairs do we have on the central atom? 0. This is called trigonal planar. And trigonal planar bond angles are 120 degrees. So now we're going to draw in the bond polarities, and we see on the Pauling scale of electronegativities that oxygen is a little more electronegative than nitrogen, but that chlorine and nitrogen happen to have the same electronegativity value. So when we draw the bond polarities, we're going to have the arrow pointing from nitrogen to oxygen, but then we're just going to have a bond with no arrow on it to chlorine. Now our last stage is to determine the molecular polarity. Right, so we're going to look at the fact that we have two different terminal atoms here. We have a chlorine atom and an oxygen atom on nitrogen. So that makes the molecule polar, so we'll say yes. Even though we don't have any lone pairs on nitrogen, it's still a polar molecule. Okay, let's go on to the next example, which is nitrate. Now let's start off with nitrate, just adding up the valence electrons that we see in the formula for the atoms. We have nitrogen, which is in group 5, so it has 5 valence electrons. And then we have oxygen, which is in group 6, so it has 6 valence electrons for each one. So that's 18 valence electrons for oxygen, and if we add all of these up, we get 23. Notice that's an odd number. Now, if you ever add up the valence electrons and you find yourself with an odd number, you've missed something. Either you've added incorrectly or you've missed something else. Notice that nitrate has a -1 charge. That -1 charge means that there is an extra electron on the formula beyond what the valence electrons for the atoms are. So if we have a negative charge, that equals 1 extra electron. If we had a 2 negative charge, it would be 2 extra electrons. If we had a 3 negative charge, it would be 3 extra electrons. Now, what if we had a positive charge? That would be 1 less electron, and so on. So let's add these up. We have now a total of 24 electrons because of that extra electron. Now we're going to figure out the central atom, which happens to be nitrogen. And then we have 3 terminal oxygen atoms connected to that nitrogen. So it looks like this. Now we're going to complete the octet around the terminal atoms. So each oxygen now has 2 electrons because of the bond. We're going to complete that. So it goes 2, 4, 6, 8. 2, 4, 6, 8. And then 2, 4, 6, 8. Okay, so now we have an octet around the terminal atoms. Notice, though, that around nitrogen there is not an octet. It only has 6 electrons around it. So what do we do in this situation when the central atom doesn't have an octet? That's right, we share electrons from the terminal atoms to the central atom to give it an octet. Now we have the 3 terminal atoms here. They're all identical and they're all capable of sharing an electron pair. So for example, I could share the electron pair from the top oxygen like this to form the double bond. And if I did that, I would have the double bond between the nitrogen in the center and that oxygen up top like this. But I could have also chosen one of the other oxygen atoms to form that double bond with. And if you do that, you will actually be able to draw 3 different structures. We call those structures that are equivalent, but with different placement of electrons, we call them resonance forms. So I'm only going to show 2 of the resonance forms here, but there's a third one. Now, one final thing to note is when you have a charged structure like this, you're supposed to put brackets around it and show the charge outside of the brackets like this. Okay, now that we have an accurate Lewis structure, let's predict the shape using VSEPR theory. We have 3 terminal atoms and no lone pairs on the central atom, so this one again is a trigonal planar geometry. And we know that trigonal planar has bond angles of 120 degrees. And we can also predict the bond polarities. We have nitrogen and oxygen atoms, and oxygen is slightly more electronegative than nitrogen, so we're going to draw the arrows in each case pointing towards oxygen. Okay, now for the last column, molecular polarity. It turns out for ions, we don't consider the polarity for ions. That's because they're charged. So we're not going to actually have a space to fill out when you see this on the worksheets. We're not going to have a space for you to fill in something on molecular polarity when you have a charged compound. So again, we do not determine polarity of ions. All right, let's go to the last page and do a few more examples. Okay, so let's do a few more examples here. What I want you to do is go through the next several examples. Actually, the last one I'm going to change a little bit. I want you to do a different molecule. I want you to do N3 actually, N3 negative. So this is called azide. And I want you to do that. So it has 3 nitrogen atoms and a 1 negative charge. I think it's a little more interesting than the SF2. So what I want you to do is go through the table, see if you can complete it, and then I'll show you my solutions here. I'm pretty much going to just keep quiet and then draw all of the stuff so you can check your answers. I might make a few verbal notes here and there if it's something I think is important. All right, so go ahead and give that a try. So notice here we have the 2 terminal oxygen atoms connected to the central sulfur, and we have 18 total for valence electrons. Drawing the structure as it is now, we've used 16 valence electrons, and we've completed the octet on the terminal atoms. We still have 2 more electrons to place. Where are those going to go? Well, that's right, they have to go on the central sulfur. So let's draw them there. So this is our 18 electrons now on the entire structure. Notice that the central sulfur, though, only has 6 valence electrons around it. So we're deficient 2 electrons. That means we're going to need to share electrons from the terminal atoms, one of the terminal atoms, to the inner central atom. So we could say, for instance, draw an electron pair in a double bond on the left or on the right. And we would get 2 different resonance structures that way, with a double bond on the left or a double bond on the right. So I'm just going to draw one of those here. So notice when we do that it doesn't change the fact that there's still a lone pair of electrons on the sulfur in the middle. That lone pair is still there. We've just added a double bond from the oxygen to the sulfur. The reason why is we had to give that sulfur another pair of electrons to share from the outside in to complete the octet on sulfur. So we have, on the terminal atoms, we have 2, and then we have 1 lone pair on the central atom. This predicts a bent geometry with 3 things around the central atom, number of 3. That gives us 120 degrees for the bond angles. Sulfur and oxygen, the electronegativities are polarized towards oxygen, so we'll draw the arrows in that direction. And then, is the molecule polar? Yes. The reason why is we have a lone pair of electrons on sulfur. Okay, so for phosphorus oxychloride, I'm actually not going to make too many notes here. Just go through the same process. So add up all the valence electrons and then connect the terminal atoms, complete the octets on the outside, and then determine the molecular geometry. Okay, so for azide, let's start by adding up the valence electrons for the 3 nitrogen atoms. Each nitrogen is in group 5, so we have 5 electrons from each, so that would be 15 from nitrogen. Notice that's an odd number again, right? We need to have even numbers for our valence electrons. Where does the next electron come from? Well, it comes from the -1 charge. We have a -1 charge, so there's 1 extra electron, so we get a total of 16 valence electrons. Now, of course, all the atoms are nitrogen, so nitrogen is the central atom, of course. And then we're going to connect the other 2 nitrogen atoms to that central nitrogen. Then we're going to complete the octet around the terminal nitrogen, so we get 3 lone pair electrons around those. Notice that the nitrogen in the center, when we do this, right, we've used all 16 electrons. If we add up the outside, it's 8 on 8, that's 16, but the central nitrogen doesn't have an octet. So it only has 4 electrons around it. What does that mean? It means we need to share electrons from the terminal nitrogens to the center to give us that 8 electron count. So we can share a pair of electrons from each nitrogen. That would be 4 total being shared, or 2 sets of double bonds. So we would have a new structure drawn where we have double bonds on the left and on the right. So let's redraw this with the double bonds in place and the lone pairs in place. Remember, we're taking 1 lone pair away from each of those terminal nitrogen atoms, so they will now have 2 instead of 3. So if you look at this, each one has an octet, and we've still only used 16 electrons. Don't forget to put the brackets around the ion with the charge on the outside. Now, because we have 2 terminal atoms and no lone pairs on the central atom, that gives us a linear geometry with bond angles that are predicted to be 180 degrees. Now, all of the nitrogen atoms are identical as far as their electronegativities are concerned. So when we're drawing the bond polarity diagram, we just draw all of the nitrogen atoms connected, but we don't have any arrows pointing towards one or the other because they're identical in terms of their electronegativities. Now, what about the molecular polarity? Well, for that, remember, we leave it blank for ions. Okay, so now you should have a pretty good understanding about how we draw Lewis structures and how we use VSEPR theory to predict the shape of those Lewis structures in 3 dimensions. So now you should be able to complete the worksheets that we have available for you in the laboratory manual. Complete those worksheets and then check your answers against the keys that we've provided for you. If you do that, you will be well prepared to take the quiz that we present to you in the lab on this material. Please let me know if you have any questions, and I will see you soon.